Okay, so good morning, everyone. Welcome to the day 3 of the 5th Indian SAT SMT school. So today we have Gautam Muduganti. So he is doing his part-time PhD at Department of Computer Science in IIT Hyderabad. He is working in industry, I think, for about 5-6 years now. Is that right, Gautam?
I just reached 10 this year. It's been a while.
Oh, that's good. So it's even more industrial experience. Okay, so I think that without any further delay, I'll hand it over to Gautam. So yeah, Gautam is all yours.
Thank you for the introduction. In today's session, I'll be talking about our technique and tool called GPU repair, which essentially automatically repairs GPU kernels. This is scheduled to be published in WIMCAI 2021 in January. Okay. I am sure all of us have encountered GPUs in one form or the other in our lives, right? But what they essentially are full-fledged parallel processing compute units, which work on the concept of SIMD, where a single instruction is executed across multiple data elements to provide an output. And this is done in a lockstep manner, which means that all of these happen at the same time across multiple GPU cores. The unit of execution in a GPU, where in this lockstep semantics, is called a warp. The way this parallelism is achieved is through threads, which run on a GPU core. A GPU core consists of a processing element and some private memory. These threads are grouped into blocks, and these blocks are grouped into grids. The left-hand side of this diagram represents a logical hierarchy of parallelism, and the right-hand side represents the actual physical architecture of parallelism that we have. Note that these block sizes and the grid sizes can be bigger than the size of the warp. And for ease of programming, these can be represented as three-dimensional arrays with X, Y, Z dimensions. Now, since GPUs deal with parallel processing, the most common cause of errors in such programs are data races. Let's take an example. In this code snippet, what the program is essentially trying, where every thread is trying to read an element from the array, which corresponds to the next thread, and then replace its own array position with that element, right? So it's a very simple program where if I take this as an input, and if I take a particular thread, it's trying to read this element and replace it with this. So that's essentially what it's trying to do. Now, since these happen in parallel, there can be multiple executions of this program. Let's take one example, right? In this example, thread 0 and thread 1. So we have two threads, thread 0 and thread 1. I'm not considering the other threads for simplicity. Now, thread 0 is reading the value of the next element in its temporary variable. Thread 1 is doing the same, and then it is replacing A0 and A1 with 20 and 30, right? So 20 is moving here, 30 is moving here. So this is one possible execution. Another possible execution is this, where thread 1 runs first and finishes its complete execution. So 30 has moved here. And now when thread 0 starts its execution, it now sees 30 in this position, and then it tries to copy it over here, giving us 30 and 30. Now, which one of these two outputs is correct? And in fact, there can be multiple such outputs. This ambiguity in parallel programming is called a data race, and this also happens with parallel programming in CPUs as well. To solve such problems, GPU kernels have a construct called a barrier. A barrier essentially forces all the threads to synchronize at this point. So if I apply a barrier at this code location, all the threads are forced to read the element first, and then they start replacing it, giving us a consistent output, which is what we expect, 20, 30, 40, so on, right? So this is one class of problems. The other class of problems that exist in GPUs are barrier divergence. This comes from the fact that they run at lockstep semantics. Now, let's take this particular example, which is run in parallel by multiple threads. As you can notice, only the even threads are going to hit the barrier. So after a while, all the even threads are going to wait at this barrier construct, but the odd threads are never going to reach it, resulting in a deadlock. This problem where the barrier is not reached by all the threads is called a barrier divergence problem. So the solution in this case is basically just to remove the barrier because there is really no race here. Now, what GPU repair tries to do is that given an input GPU kernel, it tries to identify all the data races and barrier divergence and return a repaired kernel with the least number of barriers that are enabled in it. The reason why we want to minimize the number of enabled barriers is because barriers have a performance penalty. So the less they are in the program, the better it is for performance. Now, the way we do this is we take a CUDA or an OpenCL source program, send this to Clang and Google. Clang essentially converts the C++ code into LLVM bytecode, and Google transforms the LLVM bytecode into a Boogie program. This Boogie program is instrumented. I'll be talking about how instrumentation happens in the next slide, but it is instrumented to give us an instrumented program, which is fed into the core GPU repair module. GPU repair then takes this as a repair candidate and gives it to GPU verify, and the verification result obtained from this is analyzed by GPU repair. And if there are no errors, we have our repaired program. If we see assertion failures, then we exit the program saying that we cannot fix it, and this is beyond the scope of our tool. However, if we encounter data races or barrier divergence errors, we generate clauses from them, and then we send it to a solver. If the solver cannot solve those clauses and results in an unsat, we have an unrepairable error. That means however whatever the positions of the barriers are, we cannot fix them. However, if the solver gives us a solution, GPU repair takes the solution and then generates the next repair candidate for GPU verify. This process goes on until we have a conclusion there, right? So what we essentially are doing is we are using a counterexample guided repair synthesis approach. And though we mentioned GPU verify in this slide, in principle, any verifier can be used as an oracle. Now, coming to the instrumentation part of this, let's take an example, very simple example, which we just saw, right? Now, data races can happen only with shared variables because that is where the contention is. Private variables are all good. So the intuition here is wherever a shared variable is either read or written, we identify those lines of code and insert conditional barriers before them. Note that B1 and B2 are free here. We are not assigning any value to it. That is because we let GPU verify use any combination of values for these variables so that an error is generated. Now, let's change that example a little bit, right? I moved the write statement inside an if block where only the even threads will reach it. Like given our intuition before, barriers would have been inserted right before these two statements because this is where the shared array is being used. However, now we have a problem. If this barrier is enabled, we now see a barrier divergence error. That's again because of the if condition here, right? Now, looking at scenarios like this, we also determine that analyzing scope boundaries, such as branch statements or loop heads, is beneficial. And we introduce additional conditional barriers whenever that happens. Now, the construct that I've been showing so far is a block level synchronization statement in CUDA. We have a similar statement in OpenCL as well, but these can only synchronize at a block level. They cannot synchronize threads that are in different blocks of the same grid. However, a couple of years back, NVIDIA introduced something called CUDA cooperative groups, which allows the synchronization of threads inside a grid as well. Note that this is only possible for CUDA. There is no such construct available for OpenCL. So for CUDA programs, we introduce additional barriers with barrier variables, which facilitate grid level synchronization. However, grid level synchronization has a performance penalty compared to block level synchronization. So we try to avoid them whenever possible. Now, coming to the repair algorithm that we have, right? I just took the same instrumented code that I just showed before, and we now show how repair works. This is the instrumented program, and this is sent as a repair candidate to GPU verify. Let's say that GPU verify in the first iteration identifies a data race. We then explore the SMT model returned by GPU verify to see what are the assignments that cause the data race. Let's say that they are B1 false, B2 false, and B3 false. Basically, all three of them were disabled, and we then saw data race. Now, the intuition here is that enabling any one of these barriers should cause the data race to disappear. So we generate a clause saying B1 or B2 or B3, which says that enable one of these barriers. We then send this to the solver, and the solver returns, let's say B2 is true, right? All of this kind of depend on the practical approach. I'm just taking one possible way in which GPU verify could go. Now, since B2 is true, we generate our next repair candidate where this barrier is enabled. And then in iteration 2, let's say GPU verify identifies a divergence, and that is because the B2 was set to true. Now, since this is a divergence and this is the variable which was true in the SMT model, we have another clause, which is negation of B2. Now, these two clauses are now sent to the solver, and let the solver come up with a solution where B2 is false, B3 is true. So now we have our next repair candidate where this barrier was disabled and this barrier was now enabled. Now, when this is sent to GPU verify, there are no errors because no matter whatever is the assignment of B1, there is no data race or barrier divergence. So now, since we have a repaired program, we then remove all the barriers that were free because we want to minimize the number of barriers. And then we claim that this is the repaired solution for the input program. Now, so far, we have not really spoken about the solver. We have not mentioned that it's a SAT or an SMT solver, but the way we do this is we have two strategies for implementing the solver. One is the max SAT strategy. I'm sure by now all of us are familiar with the SAT solver, which takes a bunch of clauses and determines whether these clauses are satisfiable or not. Right? Max SAT is an extension to that problem, which need not have to satisfy all the clauses. It tries to satisfy the maximum number of clauses that it can. An extension to that is the partial max SAT problem. In the partial max SAT problem, we have two categories: hard clauses and soft clauses. The hard clauses definitely have to be satisfied, and the solver tries to maximize the number of soft clauses that it can satisfy. Coming back to our problem, the clauses that we get from GPU verify are given as hard clauses, and the negation of all the barrier variables are provided as soft clauses. That is because we want to minimize the number of barriers that are enabled. So maximizing this will always minimize the number of barriers that are enabled. The MaxSat solver then tries to solve this and gives us a solution. So the other strategy that we have is a minimal hitting set strategy. Note that this is minimal and not minimum. This strategy is essentially a set cover problem where we try to use a polynomial time greedy algorithm along with unit literal propagation. Let me explain this with an example. Let's say I have these 6 clauses with me. Now, what the greedy algorithm tries to do is tries to assign a value to one of these literals such that the maximum number of clauses are satisfied. In this case, it would be B2 as true because that would satisfy 3 clauses in one go. Now, because of unilateral propagation, this enforces that B5 must be false. And now, since B5 is false, we still have 2 more clauses that need to be satisfied, and setting B6 as true would solve this. Note that this is not complete because this has positive and negative monotone clauses. So there are scenarios where this can give a wrong answer as unsat as a wrong answer, but there could be a solution. So whenever that happens, we fall back to the MaxSat algorithm to confirm that there is no solution possible. And also this strategy has a performance gain compared to MaxSat because MaxSat is more expensive than doing this greedy algorithm. Now, coming to our tool, to evaluate how well performant our tool is, we use a total of 748 benchmarks, out of which we have introduced 26 of them. All the others are available in the public domain. We compare our tool against another tool called AutoSync, which is the only other known tool that tries to repair GPU kernels. However, AutoSync can repair only CUDA kernels. So the comparison that we have between these two is only for them. OpenCL kernels, repairing OpenCL kernels is an exclusive feature for GPU repair. Right? So like one interesting feature of GPU repair is that it also inspects the given program to see if there are barriers that are not needed. Since barriers have a performance penalty, removing unnecessary barriers improves the performance of the program. So there are instances where GPU repair suggests that barriers in the given program are not necessary and removes them or optimizes them by either changing from grid level to block level barriers or removing them from loops. So that is a feature that AutoSync does not support. So that is something new for us. Also note that AutoSync errors out a lot more compared to GPU repair. That is because of the way AutoSync is implemented. It uses source code for its source code as its initial point rather than GPU repair, which uses a boogie program. That makes it very fragile to code syntax. Right. Also, there's another reason where AutoSync uses text parsing on the GPU verify output messages. And even if there's a slight difference in the output message, there is a problem. GPU repair, on the other hand, uses the SMT model, which is more robust and more standardized. Right? Also note that GPU repair repairs a lot more kernels compared to AutoSync. And it is also the only tool that can repair using grid level barriers. And GPU repair also times out a lot lesser than AutoSync. Here is a runtime comparison between both the tools. Notice that GPU repairs is slightly less performant than AutoSync for simpler benchmarks. That is because of the overhead where it has to inspect whether barriers are really needed or not, and also the slight overhead of instrumentation. However, when a repair is genuinely required, or GPU repair performs much better. And that is because either AutoSync errors out or times out or takes more time in general. Anything below this line shows that AutoSync is better than GPU repair, and anything above this line shows that GPU repair is better. So all of these are benchmarks which either time out or error out compared to GPU repair. Right. So that's all I have for today. I do implore you to go out, try it out too. Our paper is available in its preprint version on archives. Our source code is also available on GitHub. And we recently submitted our artifacts for WebKite 2021 for evaluation. You can download them. It takes like around 15-20 minutes to get set up. And you will be able to use GPU repair on your GPU programs. Having said that, I now open for questions. If there is anything that I can answer or clarify, I will be happy to do so.
Hi, Gautam. This is Subodh from IIT Delhi. Thanks for a very good talk. I just wanted to understand why are you classifying barrier divergence as an error type? Because as far as I understand, barrier divergence in most cases leads to bubbles in the instruction pipeline. Does it also lead to silent data corruption?
It leads to deadlocks. So let me hold on. Let me actually go back to the earlier slide. Yeah. So taking this example, right? So, or actually taking this example, since only even threads reach this barrier, and the odd threads don't, what a GPU enforces is that it makes the even threads wait until the odd threads reach this barrier. And since the odd threads can never reach it, it results in a deadlock. So
Uh,
that is the problem that we're trying to solve.
so yeah, so that's true. But is that at the level of the specification of sync threads, or is it also at the level of implementation in CUDA and OpenCL?
It is also in
I see.
implementation.
I see.
There are instances where deadlocks can happen
Great.
because of
Thanks.
this.
Thanks.
So actually this problem occurs because of warp. So all the cores inside a warp have a single program counter, right? I mean, because of this SIMD thing. So now if you have some thread which hits the barrier and some other were not, and now the instruction states that all of the threads that are there has to hit the barrier. Now, you have a situation where you can't proceed because there are several threads which can never hit the barrier.
Right.
So for example, if the concept of warp is not there, if this kind of a lockstep execution is not there, then this problem would not occur. But yeah, so.
Okay, thanks.
Okay, any other question from anyone? Okay, so yeah, thank
Okay.
you, Gautam, for this nice talk. I would request
Thank you, everyone.
Priyanka. So Gautam, I think if you stop sharing your screen, and maybe if you stop your video, I request the next speaker, Priyanka, to please share the screen. And
Saurabh, I don't have permission to share the screen.
You can make her the co-host, Saurabh.
okay, I think now you should be able to do that.
Um, I'm so sorry, but I am actually using two systems, and I want you to make me host for the other one, just to see the chats and everything. So I'm so sorry about this. The one, I think it's unmuted.
Okay, I see. Okay, can you please try now?
Yes, thank you. Just a minute. Okay, I'm ready to go.
So just 1 minute. So can you also, so which of these account has your video, if I may ask?
My video is turned on, right? Or is not?
So is it the same account where the screen share is there? Or
Yes,
different?
yeah, it's the same account. Yeah.
Okay, yeah, so it's good. So let me check the stream is fine. And just give me a second. Okay, I think what is happening is that in the stream, your video is not coming. I think there's some. Oh, okay, yeah, now it's fine. Yeah. Okay, so good morning, everyone. Again, we have our next speaker. So Priyanka is a joint degree PhD candidate, both from IIT Kanpur and National University of Singapore. Her research advisors are Dr. Shubhajit Roy and Dr. Kuldeep Neal. So we have already heard Kuldeep yesterday. Her research interest lies in the area of Boolean function synthesis, constraint solving and sampling, and knowledge compilation. And now she's going to talk about her work in that was accepted, that was presented in CAV 2020 about a data-driven approach for Boolean function synthesis. So yeah, over to Priyanka.
Hello, everyone. Thank you, Saurabh, for the introduction. So I'm Priyanka, and I'm going to talk about Manthan, a data-driven approach for Boolean function synthesis. This is a joint work with Kuldeep Neal and Shubhajit Roy. This work has been published at the International Conference of Computer-Aided Verification, CAV 2020. So let's get started with the introduction to Boolean function synthesis. So we have given a Boolean relation, f, between the set of input variables x and the set of output variables y. Our objective here is to synthesize a function with respect to every output variable. That is, we want to synthesize a function psi I corresponding to every output variable yi, such that if we replace y by psi of x in the relation f, it still holds true. That is, for all the valuation of x for which f of xy evaluates to true, f of x psi of x should also evaluate to true. Such a function is known as column function in the literature. Just to ensure that we are on the same page, let us consider an example. So let us suppose we have given x1 and x2 as an input variable and y1 as an output variable, and the relation or the specification between input and output variable as this, x1 or x2 or y1. So our objective here is to synthesize a column function corresponding to the output variable y1 in terms of x1 and x2. So for that, we can once rewrite this specification as negation of x1 or x2 implies y1. This is like if A implies B, then it's a negation of A or B. So it's just a rewrite. So here we can see that we can guess that this column function corresponding to the output variable y1 can be negation of x1 or x2. At this point, we don't know whether this is a column function or not. We are just guessing that this can be one possible column function. Let us try to verify whether this is indeed a column function or not. For that, first we have to compute f of x psi of x. So what we did here, we replaced y1 with the corresponding column function negation of x1 or x2 in the original specification f of xy, and we'll get this f of x psi of x. So now, as you see here, for all the valuation of x for which f of xy evaluates to true, f of x psi of x is also evaluating to true. Therefore, this is indeed a column function corresponding to the output variable y1. Now the question arises here is this the only possible column function corresponding to the output variable y1? And it turns out that there can exist multiple possible column function. For example, negation of x1 or x2 that we just discussed, negation of x1, negation of x2, or it can be as simple as constant function 1. So our objective here is to synthesize one possible column function. So that's all about the introduction. Let us move to the application part of it. So the Boolean function synthesis has application in wide variety of domain that includes certified QBF solving, program synthesis, cryptography. We will discuss one such application, cryptography, in detail. So the security of well-known encryption algorithm, RSA, depends on the factorization problem. So what is the factorization problem? Given a number x, we want to compute the non-trivial factors of x. So first, let us try to rewrite this factorization problem as a relation between input x and output y. So here we have rewritten. So it's like y divides x. Y cannot be the part of 1 and x as it's a non-trivial factor of x. The z here represents a set of integers. So now we have given a Boolean relation f, and we want to compute a function psi that takes x as an input and gives us y. And we can do it by Boolean function synthesis. So that's how we can solve the problem of factorization via Boolean function synthesis. So what is the state of the art for the Boolean function synthesis? The origin of this problem traces back to Bull's seminal work, which was subsequently pursued with the focus of decidability by Skolem. Over the decades, we have seen significant improvement in both theoretical and practical perspective. We know that there exist a polynomial instances. There exist a problem instances where Boolean function synthesis must take super polynomial time. On the other hand, the practical improvement derived from a diverse set of techniques that includes proof of validity, quantifier instantiation in SMT solver, input-output separation, knowledge representation, incremental determinization. Despite big intense algorithmic development over the decades, still there exists a large fraction of instances that are beyond the reach of state-of-the-art solvers. We, as a practitioners, believe that we can do much better. So towards our goal of having better and efficient synthesis technique, we propose Manthan. Manthan uses machine learning to come up with candidate functions, approximate candidate function. As we all know, machine learning needs data. Manthan does constraint sampling to generate the data. Later, the candidates are repaired using formal and automated reasoning. Let us look at the broader overview of Manthan. Manthan takes input f of xy. It first generates the data. With the help of data generated, it tries to learn the approximately correct Skolem function. Manthan is a sound system. It verifies whether the learned candidate functions are the Skolem function or not. If only the candidate function passes the verification check, Manthan outputs the function psi. Otherwise, candidates needs to undergo a repair iteration. Let us look into each component in detail. So the first is data generation. The problem with this data generation is we want to capture the relation between f of xy. So let us consider an example here. So this part of the example we have already discussed, and now we have conjuncted with another specification. So the data here, this table here represents all possible satisfying assignment for this specification. The highlighted rows represents that for a fixed valuation of input variables x1 and x2, there can exist multiple valuation of output variables y1 and y2, as this is a relational data. And this is exactly where this data differs from the classical machine learning data. In the classical machine learning, for a fixed valuation of input variables, we have exactly one label of output variables. But as we are trying to capture the relation between input and output variable, here we have for a fixed valuation of input variables, there can exist multiple valuation of output variables. So now, if we ask to sample uniformly at random 4 data points, we may end up getting this right-hand side table as our data points. As we have already discussed, there can exist multiple possible Skolem function for a particular specification. For this specification here, we can have a constant function 1 corresponding to the output variable y1 and a constant function 0 corresponding to the output variable y2. But with this data generated, it will be difficult for a machine learning algorithm to learn y1 in terms of x1 and x2 in a simpler form. Similarly for y2. We are talking about just the 4 variables right now. Think about the cases where we have tens of thousands of variables. We really want machine learning to give a data from which it can learn a simpler function. Suppose by some magical sampler, we end up getting this right-hand side table as our data. Notice the change here. For all the valuation of x1 and x2, we have y1 as 1 and y2 as 0. With this data generated, it will be easy for a machine learning algorithm to learn a simpler candidate function. So towards this, we propose an adaptive weighted sampling strategy to generate the data. What we do is we try to sample uniformly at random over the x variables, the input variables, in order to cover the entire domain. At the same time, we try to bias the valuation of output variables y. For that, we first sample a small number of data of x uniformly at random and y biasing towards 1 and y biasing towards 0. With those data generated, we try to learn a good bias Q for the y variables. And now, with that bias Q, we again sample x with the uniformity at random and y with the bias Q. This is the adaptive weighted sampling strategy that Manthan uses to generate the data. Once we have the data, the next step for Manthan is to learn the candidate function from the data. So again, let us take this example. And suppose this is the data that we get from the data generation component of the Manthan. So here, just looking at the label of y1, we can see that this is a binary classification problem because we have just 1 and 0. Now we can consider the valuation of x1 and x2 as feature set and y1 as label, and we can learn decision tree to represent y1 in terms of input variables x1 and x2. Let us take an example. So here, when x1, x2 is 1, that red line represents the decision node being 1. So when x2 is 1, we see that y1 is 1. And when x2 is 0, the green line represents the decision node being 0. We don't see a proper classification, so we have to go with the x1. And when x2 is 0, x1 is 1, the y1 is 0. When x2 is 0, x1 is 0, y1 is 1. So this is the decision tree we'll learn from this particular data. And now we can simply disjunct it with all the leaf nodes with the path 1, all the paths with the leaf node 1. So here we have this path x2, disjunction with this path, negation of x2 and negation of x1. So this can be a possible candidates column function for the y1. So let us try to generalize this. So here we have to learn a candidate function psi. We consider the valuation of x in a data as feature set, the valuation of yi as a label, and we can learn a decision tree classifier with this feature set and label. And the candidate function will be the disjunction of all the paths with the leaf node 1. So that's how Manthan learns the candidate function. Now, Manthan has to verify whether the candidates learned are this column function or not. Again, let us try to consider the case when the candidates are not this column function. For that, we know that there exists at least one valuation of x for which f of xy will be true, but f of xi of x will be false, right? And when the candidates are this column function, then all the valuation of x where f of xy evaluates to true, f of xi of x will also evaluate to true. So for that, for the verification of the candidate function, we construct a formula E over x, y, and y prime. The y prime is the newly introduced variables. The cardinality of y prime is same as the y. We call this E formula as error formula. So now, let us try to understand this error formula. We have in this second clause, it's the same specification, but now y is not set to y prime, and the y prime is fixed to the output of the candidate function. Now, when will this error formula will be set? So for set, f of xy has to evaluate true, and f of xy prime has to evaluate false. Then only because of this negation, the error formula will be set. That is, if there exists a valuation of x for which f of xy evaluates to true and f of xy prime evaluates to false, then error formula turns out to be set. And similarly, if for all the valuation of x for which f of xy evaluates to true and f of xy prime evaluates to false, the error formula turns out to be unset. Now, as a verification check, Manthan checks the satisfiability of error formula. If the error formula is unset, then Manthan returns the candidate function psi. If it is a set, then we have a counter example to fix. Let us assume that sigma models the error formula, then we have to fix the counter example sigma. Now, once we have the counter example to fix, the next question comes to our mind is which candidate to repair. We have cardinality of y many candidates. So out of those, which one we need to repair? So now we know that the error formula is set. And for this, the f of xy is evaluates to true, but f of xy prime evaluates to false. Therefore, wherever the sigma yi is not same as sigma yi prime, the candidate function corresponding to those yi can be a potential candidates to repair. So once we have found out that candidates to repair is yi, we try to repair the candidate yi. So the objective of this repair iteration is, for this particular valuation of input variables, currently whatever the output the candidate function is giving is not true. It's not satisfiable, right? So for which the f of xy is not evaluates to true. And our objective here is to make it to evaluates to true. So that is, if for the current valuation of x, if the current candidate function psi I is giving us 0, we want it to give us 1. And if it is giving us 1, we want it to give us 0. So for that, we construct a repair formula beta. How we are going to construct that we will see again later. But let's suppose we construct a repair formula beta over a subset of literals of sigma x. So then if we have such a repair formula beta, so just to make it from 0 to 1, we can disjunct it with the candidate function, and from 1 to 0, we can conjunct it with the negation of beta. So that's how we can repair. Now the question comes to our mind is, how do we construct such a formula beta? For that, Manthan constructs another formula called GI. So here we have in the GI, we fix the valuation of X to the current counter example, and the valuation of YI is fixed to the current output of the candidate function. It is sigma yi prime. Remember, y prime is set to the output of the candidate function. So we fix the valuation of x, that is the input variable, as the current value of counter example, and the yi as the current output of the candidate function, and then and such that we construct the formula gi. Now Manthan tries to find the unset core of this formula gi. The beta formula is constructed using the unset core of GI formula. All the unit clauses in GI, the conjunction of all the unit clauses of unset core of GI will be used as a repair formula beta. And once we have found the repair formula beta, we know that we can, depending upon the cases of 0 to 1 and 1 to 0, we can repair the current candidate function. So that's how Manthan repairs the candidate function. So let us try to take a broad overview of Manthan. Manthan takes the input specification f of xy. It first generates the data with the use of adaptive sighted sampling strategy. With the data generated, it tries to learn the candidate function using a decision tree classifier. Once it has generated the candidates, it verifies whether the candidates are this column function or not. For that, it checks the satisfiability of error formula. If the error formula is unset, it returns the column function psi. If the error formula is set, it tries to find the unset core of G of formula. Using the unset core of G formula, it constructs the repair formula to repair the candidates. This process continues until the error formula is unset. So that's how Manthan generates the column function. Let us try to look at the experimental evaluation. So we did experiment on 609 publicly available benchmarks from the diverse set that includes the QBF eval competition, arithmetic set, destructive decomposition set, and factorization benchmark. We compared Manthan over the state-of-the-art tools CADIT, BFSS, and C2SYN within a timeout of 70 to 100 seconds. So the plot here represents the cactus plot, with y-axis being the CPU time and x-axis being the number of instances solved. A point xy represents that each of the x many instances were solved less than or equal to y much time. And here we can see that the state-of-the-art tool CADIT can solve 280 instances out of 609. So where does the Manthan stand? So the green line here represents Manthan. As we can see that Manthan is able to solve 356 benchmarks, which is an increment of over 76 benchmarks with the state-of-the-art. Not only just that, it also solves 60 new benchmarks that none of the state-of-the-art able to solve. If you see this graph here, we see that the time taken by the Manthan is comparatively more for the comparative to the state-of-the-art. This is because of learning time spent in the machine learning and the data generation process. So that is all about the experimental evaluation. It also opens up the interesting future directions. Like we propose one of the strategy to generate the data, that is the heuristic-based adaptive weighted sampling strategy. But we still don't know what will be the ideal distribution to generate the data. What will be the ideal distribution to capture the relation between the between the input and output variable. We are talking about the candidate function, but we don't know how good are the candidate function generated by the data. We don't have a qualitative or quantitative measure to measure the goodness of the candidate function. So we, as we all know that the candidates learned by the machine learning are not the abstraction, these are the approximations of the original candidate function. That is, we have the both sided error. It can be 1 to 0 and 0 to 1. So we are moving from abstraction to approximation in the verification. And another thing is, can we use the similar kind of approaches for program synthesis and program repair strategies? So with this, I would like to conclude my talk. So in this talk, I presented Monon, a data-driven approach for Boolean function synthesis. Monon uses constraint sampling to generate the data. With the data generated, it uses decision tree classifier to learn the approximately correct candidate function. And later, the candidates are repaired using formal and automated reasoning. With this approach, Monon is able to solve 356 benchmarks over the state of the art to where the state of the art was 280. It also opens up several interesting questions and directions. The tool is open source. Please give it a try. Thank you. I'm open to take a question.
Okay, so thank you very much, Priyanka. Is there any question?
Yeah, excellent talk, Priyanka. Just one little question. So for the factorization benchmarks, Manthan is, I mean, can you tell us where Manthan is on those?
Unfortunately, Monon is not very good on factorization benchmarks.
Yeah,
Up to 14 bits, it is able to solve.
I see. And any insights you might have on, I mean, this these benchmarks turn out to be hard for all of the tools. So,
Um,
have any insights on, why the data-driven thing did not work for factorization?
Maybe the data generated is less. Like if we increase the data, then it might be able to capture the relation between those. So right now we decide the number of data according to the cardinality of y variables, but might be because it's a bitwise thing. So it needs more data to come up with a good candidate function.
Okay, thanks. Yeah, excellent talk.
So I have a question. So during your, since you mentioned there could be multiple Scholar functions, is the length of the description of the function, does it appear anywhere in your search, maybe some inclination towards shorter description function? Or
Yeah, that we might look into, but the current version of Manthan doesn't uh, consider that as a factor. So it just try to find one possible column function irrespective of the length or anything.
because I believe in your last slide you mentioned one of the question, but yeah, perhaps I think the length of the description could be one measure of goodness of function, if I may say so. I'm
Yes, yeah.
following the principle of Occam's razor. Maybe that's okay. So
Yeah, so just to jump in, I think you are right, Saurabh, in the sense that if the description is large, then it would not be possible to learn using very small number of samples. So we are using the number of samples varying between, I guess, 1,000 to 10,000 samples. And if the description is large, then those number of samples would be insufficient to learn it. So, but it would be nice to also characterize it more formally.
but so right now, does your current search procedure take this into account anyway? Somehow, bias the search toward a shorter description function?
In some sense, it does, because the candidate generation that we are using uses these decision trees, and usually kind of this standard construction of the decision tree would bias towards simpler uh, trees if possible. So they tend to reduce overfitting, and overfitting is highly correlated with larger functions.
I see. I see. Okay. So thank you, Priyanka, once again for such a fantastic talk. Now, may I request Rishabh to set up the screen and
So my screen sharing is disabled. Hello. Hello.
yeah, just give me a moment. Let me just give you permission. So now you should be able to do that.
Yes, I can see it. Okay. Can you all see the screen? Yeah.
Yeah, we can see.
So
Just 1 second. So can you also, I think, just 1 second. Let me check the stream. Okay. So we have Rishabh here now presenting about exploiting symmetry for deadlock detection in message passing programs. So Rishabh is a third year undergraduate student at IIT Delhi, and he is working with Subodh on this. So over to Rishabh.
hello everyone. Thank you, Saurav, for the introduction. As Saurav said, I'll be presenting my project on exploiting symmetry for deadlock detection in message passing programs, which was done under the supervision of Professor Subodh Sharma at IIT Delhi. Distributed programs written using the message passing paradigm are prevalent across domains such as scientific computing and high performance computing. These programs are often not written by CS professionals, but by professionals affiliated to other scientific disciplines. These suffer from the curse of deadlocks, which are an important class of bugs for message passing programs. They are easy to introduce, but hard to detect. Traditional testing methods fail on deadlocks, and these programs are often run on large clusters, so the manifestation of deadlocks during deployment can be very expensive. Message passing frameworks often provide non-deterministic communication primitives, which makes verification hard. The problem is undecidable in general, but even for terminating programs, it has been shown to be NP complete. On the right, you can see the skeletal communication structure for a simple message passing program. It consists of three processes, P0, P1, and P2. P1 has sent, P1 and P2 have sends to process 0, and P0 has two receives. One of these receives has a star. This denotes a wildcard receive. A wildcard receive has a wildcard receive is allowed to receive from any sending process which is sending to the receiving process. So it's not constricted which process it receives from. For a given MP program, we can define a trace as a sequence of matches which are allowed by the MP semantics. I'm not going to go over the MP semantics here, but they are mostly intuitive. So let us look at two traces here. The first one is a non-deadlocking trace. Here, the send from process 1 first matches the wildcard receive at process 0, and then the send from process 2 matches the receive at process 0. But in an alternate scenario, the send from process 2 could match the wildcard receive at process 0. And in this case, the send from P1 and the other receive from P0 would remain unmatched. And this is therefore a deadlocking trace. The existing approaches for verifying MP programs are as follows. In symbolic verification, the entire program is represented symbolically. This provides a good coverage of the input space as long as the input space can be captured symbolically. However, it is not scalable. An example for this is MPI-SV. The other approach is for dynamic trace verification, where the program is run and a dynamic trace is generated, which includes the events from the message passing framework. And then this trace is verified. So tools that use this are ISP, Mopper, and DAMP. This is faster than symbolic verification. However, it works. The results are strictly valid for fixed inputs only. And then there's a hybrid approach, such as Hermes, which combines symbolic execution as well as dynamic verification. It happens to be the state of the art for dynamic verification of programs with terminating execution traces. Now, among these, Mopper and Hermes are SAT-based methods. They encode the message passing program into a SAT formula and invoke a SAT solver to decide whether or not the program contains a deadlock. Now, before jumping into our contributions, let me talk about symmetry in SAT. So consider a simple SAT formula f is equal to a or b or c. A, b, c are Boolean variables. And there are a total of 7 solutions for f. However, we can see that f is symmetric in a, b, and c. More formally, for a and b, if we just swap them, then f remains the same and therefore the satisfiability is preserved. So if ABC is any solution of f, so is BAC. Now, because of this, we can add some symmetry breaking constraints, preserving the satisfiability but reducing the solution space. So in this case, A or not B is basically a simple way to encode that A is greater than equal to B, and similarly B is greater than equal to C. So you see the remaining solutions of f dash are only those solutions where A is greater than equal to B is greater than equal to C. Now, the key idea is to use this symmetry breaking in SAT solving. It happens that these additional constraints that are added for symmetry breaking allows the SAT solver to effectively prune the search space, and therefore it speeds up SAT solving. Now, a natural question arises is that if we have symmetry breaking methods, and if we have a method that can take a message passing program and encode it into a SAT formula, can we not just compose them? Well, this approach fails, and we have tried this using the existing symmetry pre-processing tools such as Breakit and Shatter. What these tools do is that they take the SAT formula, they detect and encode the symmetry into an additional SAT formula, combine it with the original SAT formula to get a new formula, and then feed it to the SAT solver, expecting a faster solving time. However, the formula that is generated by Hermes or Mopper is large. And because of this, the pre-processing time is unreasonably high. We also did not see much gain in the solving speed of the pre-processed formula. And the reason why this fails is that it fails to use domain-specific information, which was used to actually generate the SAT formula. It uses the information that is available only in the SAT formula. So our solution to this is that we detect the symmetries from the program itself and then use symmetry breaking encodings and feed it to the solver. So our contribution is that we realize that symmetry is very common in message passing communication patterns, and this introduces verification redundancies. For instance, in the master worker pattern, which is very common, the master communicates with each worker very similarly, and therefore it is somewhat redundant to have to verify the communication between a master worker pair for each worker. But the question is, how do we characterize these symmetries and how do we detect these redundancies? So this is the contribution of our work, that we give a theoretical framework for taking a message passing program and detecting and leveraging these symmetries in the form of symmetry breaking constraints, which allows for faster SAT solving. We implement this in a tool called Symmetry, which allows the deadlock detection of C or C++ programs written using the message passing interface MPI. So to whet your appetite, let me show you some of the results we obtained. We used benchmarks from the FEVS benchmark suite, which is a functional equivalence verification suite for high-performance scientific computing by Stephen Siegel, and some benchmarks from Hermes. In this, the timeout was set to be 60 seconds. And these benchmarks are meant to represent real-world communication patterns, such as the master worker pattern, the grid or the torus topology, and multiple control flow paths. And as you can see, Symmetry was able to outperform Hermes on all of these benchmarks. With the increasing number of processes, Hermes timed out, but Simian scaled a lot better. And this happens for all of these benchmarks. So coming to our methodology, here's a motivating example. Consider a program with 3 processes, P0, P1, and P2, where P0 is sending to P1 and P2 and then has 2 wildcard receives. P1 is receiving from P0 and then again sending to P0, and similarly for P2. A sample trace for this program would be as shown here, that the sends match the receives and then the other sends match the wildcard receives. Now, because P1 and P2 are symmetric, we could have an equivalent trace tau dash by replacing ones with twos and twos with ones in the process indices. And since if this is a valid trace which is non-deadlocking, then this is also a valid trace which is non-deadlocking. And in the similar manner, we could have a lot of equivalent traces in message passing programs, and these equivalence classes do not need to be verified completely. So the idea is that we want to reduce the search space to contain only one or a few representatives of each class of equivalent traces. How do we do that? To extract symmetry, we use graph automorphisms. First of all, we construct a program graph from the given message passing communication structure. The program graph has nodes for each of the communication events, such as sends and receives. Further, it has directed edges, which represent the matches before order, which is imposed by the MPI semantics. And it also has undirected edges, which are shown here by dashed lines, which represent potential matches. So the sends and receives can match. And here you see that the wildcard receive can match either this or this. From this program graph, we extract an automorphism. So here's a sample automorphism for illustration. So an automorphism is a function from E to E. Here E is the set of events. And in this case, this sample automorphism, we are mapping S01 to S02, S02 to S01, and so on. Note that phi, this automorphism phi, when applied to tau of the previous trace, gives tau dash, because it is essentially doing the same thing, swapping process indices 1 and 2 at the call level. So further, we define automorphism of traces. An automorphism of traces is again a function from events to events, which preserves the deadlocking behavior on all traces. So for instance, phi preserves the deadlocking behavior on tau, as I said in the previous slide. But if this happens for all the traces, then phi would be said to be an automorphism of traces. And the key result that we prove is that the automorphism group of the program graph is precisely the automorphism group of traces. The automorphism group of traces is what we want to implement symmetry breaking constraints. And the automorphism group of program graph is what is computationally possible, because it allows us to reduce the problem into the problem of graph automorphism. Graph automorphism is a very well-studied problem. The automorphisms of a graph form a group, and a group can be described by generators, which are at most linear in the graph size. This comes later when analyzing the size of the formula generated. No worst case polynomial algorithm is known, but it is very efficient in practice. The expected runtime for graph automorphism is linear, so it is quite fast for real world use cases. And I would also like to point out that Brackett and Shatter also use graph automorphism. However, the input graph that they feed to the graph automorphism solver is orders of magnitude larger than ours, and that is why they fail. Now coming to the SAT formulation. The SAT formula that we use has 3 different parts: the trace encoding, which encodes the MP semantics And the solutions for this part correspond to valid traces, the safety constraints, which are satisfied by deadlocking traces, and finally, the symmetry breaking constraints, which reduces the search space while preserving the satisfiability of 1 and 2. 1 and 2 are from previous work, 3 is our contribution. So for illustration, let us look at the SAT constraints from MOPR. So some of these constraints are for the validity of traces, some other constraints are for deadlocks, and the solution to the entire formula would be a deadlocking trace. There, as you can see, I won't go into much detail, but there are variables corresponding to calls and pairs of calls. So the subscripts are calls, and if you see SAB, then it means that S is a variable corresponding to a pair of call A and B. And similarly, there are some calls which are single indexed by one single call. And as you can see, there are constraints corresponding to different semantics. So there are constraints to enforce the partial order. There are constraints that make a unique match for send and receive. And coming to deadlock constraints, there's this constraint not all matched, which says that in this trace, all calls have not been matched, and therefore this must be a deadlock. How do we add symmetry breaking constraints to this? So for simplicity, let us consider only the S variables and not the other variables from the previous slide. And we write the solution for the SAT formula as a bit vector of the valuations of the variables. The result we show is that if phi is an automorphism of traces, then this bit vector, when we transform it by moving the variables around using this, that's that SAB goes to S phi A phi B, then this is also a solution. And because of this, phi induces an equivalence class of solutions. So we do not need to search for all the solutions. So we post Lex leader constraints, which simply says that the bit vector on the left should be greater than equal to, in the lexicographical ordering, than the bit vector on the right, which is obtained by shuffling the values using phi. And to encode this Lex leader constraint as a SAT encoding, we use this formula, where if m and n are size n bit vectors, then this formula simply enforces that m is lexicographically greater than n. It uses these additional variables x to reduce the formula size by substituting common sub-expressions. And this follows the very similar logic as what you would do for lexicographically comparing bit vectors. Soundness of symmetry breaking constraints would mean that at least one representative from each class is a solution. Completeness would mean that only one representative from each class remains a solution. For completeness, we could use all automorphisms as phi in this Lex leader constraint and post multiple Lex leader constraints. However, these automorphisms may be exponential in number. So we just use generators, which are linear in number. They are complete in some common special cases, and even in general, they give us good quality. And because of this use of generators and this encoding shown on the left, the size of the symmetry breaking formula is asymptotically same as the size of the original formula. So we are not adding a lot of bulk to the formula. Now, these things work well for simple theoretical cases, but in real world programs, we do not really have overall symmetry very often. You'll often see things like there's an asymmetric portion, and then it flows to some other symmetric portion. Then it might be repeated due to the
maybe yes, next 3-4 minutes if you can wrap up.
Yeah, I'm just winding up. So there can be these repeated symmetric portions due to loops or recurrent communication behavior, and there can be different kinds of symmetric portion. So to extend to this, we introduce communication epochs, which we prove the theorem that the strongly connected components of the program graph can be verified independently. And so what happens is that a big program graph is split into smaller parts, and each part can undergo symmetry breaking separately and verification separately using different calls to the SAT solver. And these epochs can also be cached. Further, we can also extend it from single path to multipath programs. Single path programs have a control flow which is independent of the communication, whereas multipath programs can have multiple control flows depending on the interprocess communication. And this also uses SAT for path feasibility checking. And this is an important bottleneck. So we also extend our symmetry and epochs methods to drastically reduce the SAT solving runtime here as well. So this concludes my talk, and this is the tool flowchart for reference, and I'll be open to questions. Thank you.
So are there any questions from the audience?
No.
Yeah, excellent talk, Rishabh. I had one question, which is maybe at a slightly higher level, which is so if you did not put in the symmetry breaking constraints, do you think? I mean, basically, is the benefit that you're getting attributable largely to the symmetry breaking constraints, or are there other things happening?
Okay, let me go to the slide on this. So I'm sorry. Yeah. So the benefits of the symmetry breaking constraints are seen mostly when the number of processes start becoming large. And that is because I'll take a simple example. So if you have a master worker pattern, if you have a master worker pattern and say there are n workers, then there can be n factorial permutations among these workers.
No,
Right?
I understand why the symmetry breaking constraints are really serving a big purpose. I'm asking, are there other things which are uh, also combining along with the symmetry breaking thing? Uh, you know,
Yes.
yeah. I
It's
would like to know about those. I mean, symmetry breaking clearly helps. That is clear.
So symmetry breaking helps, but all these benchmarks which I showed, most of them won't just be amenable to symmetry breaking directly. That is because, as I said, the overall program structure does not have symmetry always. But if you can break it into communication epochs which are independent, then it breaks the program graph into small parts. And these small parts are often corresponding to communication structures which are present in the program. So you might have a big program, but a small portion of that program might just be doing a simple broadcast communication where a master is communicating with each workers. So if you can isolate that, and then you can apply symmetry breaking on that. So a small portion which was going to take a lot of time in the SAT solver is now solved very fast. So when both of these methods are combined, that you break it into independently verifiable epochs, and you apply communication symmetry on all these epochs, then it works very well. And actually symmetry plays a big role because the scalability, we can see that it does not rise as fast. Like in ordinary cases, there will be programs that you would expect to the runtime to rise exponentially, but because of symmetry, since we are removing the redundancy, it's not rising as fast as that.
So
Okay, so essentially what you're saying is there are other things that are enabling you to find sub problems where there is symmetry, and then you apply symmetry breaking over there, right?
Yes.
So finding sub problems, okay, that makes sense. Okay, great.
uh, yes, I also excellent talk. I had a similar follow-up question. So I did not get. Are you able to divide into these sub problems automatically, or you have some sort of um, manual information that you are feeding in?
No, we are being able to divide into these sub problems automatically. So there was a bit of detail that I glossed over, but these edges which represent the potential matches, they need to be computed. Now, computing an exact set of potential matches is NP complete, but we can compute an over approximate set of potential matches, which contains all those actual potential matches, but may also have some more of them. Now, once we have these potential matches, then we can construct this program graph. And in the program graph, we just do a strongly connected component analysis, which is a linear time graph algorithm. And that breaks the program graph into these parts, which can be proved to be independently verifiable. So the exact formulation for that theorem would be that if the entire program has a deadlock, then at least one of the epochs would have a deadlock. On the other hand, if that entire program does not have a deadlock, then none of the epochs will have a deadlock.
Oh, nice. I think a comment would be there is given a partial order, sometimes you may be interested in enumerating or counting the number of total orders, linear extensions of it. And it would be interesting if, some of this idea can be used in those problems. Where on the high level, there is not a lot of symmetry, but it looks like once you assign some variables, then the problem starts displaying quite a bit of symmetry. So that may be just a comment to look into.
Thanks, Kuldeep. We'll love to take this after the talk, maybe in session or offline, in an offline mode.
So I have a couple of questions. So one short question is that right now the analysis that you presented, is it sensitive to data and control, or you are abstracting those away?
Okay. So the analysis that I presented in the previous slides, that is for one set of events that a scheduler is giving me. And that is for a single control path, which does not depend on inter-process communication. However, in Hermes, in this paper, Dynamic Symbolic Verification of MPI programs, this method was extended to multipath programs, where we use a symbolic execution to generate all possible path conditions. And then for each of these path conditions, we can do the verification using SAT. So Simian extends the multipath case as well. So here we would have to, the backtracking algorithm which generates all the path conditions remains the same. But for every new path that you want to check, a SAT solver is used to determine whether this path is even feasible or not. And this SAT solver...
So when you say path condition, is it local to a process, or essentially in that path you also consider that some values might be coming in from other process that can determine where the control goes?
Yes, so when I say path conditions, I mean conditions on values that can come from other processes. So for instance, if you have a receive from other process and then you apply an if statement on that receive, so it branches depending on the exact value that it receives from. And that makes it multipath. So even there, the formula remains somewhat similar. There are things that become different, but they can also be handled using the same symmetry and epoch techniques with slight modifications. And this is also important because even there SAT is a bottleneck, so it does help to reduce runtime in the multipath case as well. So in this Monte, this last benchmark, which is from Hermes, is a multipath program. And as you can see that even for that, we are able to scale very well.
So interestingly, some of these benchmarks are such that if you go from number of processes 8 to number of processes 9, the SAT solver would not even return in half a day. So these results sort of, I mean, we always knew that these are highly symmetric, but we were quite happy to see that the solving gets done in sub 10 seconds.
So one last question is, I think, so for example, the GPU verify, right? It has this two-threaded abstraction kind of a thing. So the actual number of threads does not matter in some sense. And I was wondering that, once you detect these epochs, whether some of those ideas can cross over and be applied here.
Rishabh, if I can answer, if I can take up that question.
Sure.
Surely, yeah. So the idea would be to identify the number of parametric flows in a message passing program. And if one can do that, then this two-thread abstraction that you're talking about in the space of GPU programs, something analogous to that could be applied here also. So remember, this is a hybrid of dynamic and symbolic verification, which means you have to provide the number of processes, a concrete value to number of processes at the time of verification. And so we don't want to be, just linearly increasing the number of processes and keep verifying the same benchmark time and again. So in such cases, what we can do is identify the parametric flows, identify if there exists this small number k, which is representative for all the processes, or rather representative of the process flows in the message passing program. Then you can verify up to that number k, and that will give you a proof that you have verified for all processes. Yes, indeed. So it could be, so in summary, it could be done. We have not done it yet.
Okay. So thanks, Rishabh, again for a wonderful talk. And I think that, so this concludes our morning session. Our afternoon session, we have Dr. Guy Katz giving tutorial at 1:30 p.m. Indian Standard Time. I request everyone to join a little bit early, maybe 5-10 minutes early, just so that there are no issues. If there are any issues, you can figure things out on Zoom meeting, etc. So see you all. The session will start at 1:30 p.m. IST.
Thank you. Bye.